Hello. Welcome to Reflection and Refraction. Unbeknownst to you, take two. The audio on my first go was corrupted. So here we are again. Or here I am again. Let's start with reflection. So what you cannot see on this is there's little gradations of angles here. And when light comes in at 50 degrees, it hits the surface and it leaves at 50 degrees as measured from the middle here. Now, if you want to recall your mathematics, the name of a line that sticks straight out of a surface is called the normal. So, let's start with the definition of a normal. For a normal flat surface, there's a normal. And for reflection, the angle of incidence should equal the angle of reflection as measured from the normal. Now this is for a flat surface. If we get fancier with this, see your old friend the sine wave? Then the normal would be here, 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 and here. You basically zoom in so close that a complicated shape essentially is just a line, and then you draw your normal perpendicular to that line. So this may seem like kind of a silly situation, but trust me, very soon you're going to be dealing with somewhat more complicated figures that are going to look like this, or possibly like this. As a preview of coming attractions, for objects like this, when you figure out the normal, you've got to do that zooming in trick. Like so. So that's your introduction to the normal, which is what we will be measuring pretty much all of our reflection problems using, and also all of our refraction problems using. Reflection is when light bounces off. And reflection follows one mathematical rule, which is that the angle of incidence is equal to the angle of reflection as measured from the normal. Doesn't matter what kind of material you're reflecting off of, as long as the material is shiny enough to bounce any kind of light back at the wavelength you're interested in, it's reflective. So there's your mathematical law, nicely summarized. Angle of incidence equals angle of reflection. Now let's delve a little bit deeper into the idea of what reflection is. There's two basic types of reflection: diffuse reflection versus specular reflection. Specular reflection is when an object is very reflective indeed, and also very flat. So think here of your perfectly flat mirrors. Specular reflection generates a very nice pattern associated with it. Don't look directly into a green laser, but there's no harm in letting the camera look at one. So I'm going to shine this laser into this very shiny mirror, and I will hope that I can get a little laser dot showing up on that white area that I just illuminated. There we go. Extremely sharp. Diffuse reflection occurs when surfaces are rough. Rough/complicated. This is not as diffuse as I would like, but hopefully is diffuse enough to make this point. No, it really isn't. Disappointing. Well, let me show you an example of a diffuse surface that you have seen before. Here is the moon rising above a lake. Now, as you look at the lake, you see an image of the moon that's smeared out like this. Now, the water here is still following the rules of reflection. The reason that it looks like this is that when you take a cross-section of it and project it out, the little ripples on the water look like that. So some of the moonlight is coming in. And just getting lost to your eyes. Some is coming in. It's actually very hard for me to draw a picture that doesn't get lost to your eyes. And coming out this way. Some is coming in like this, and coming out this way. And so here, this is where you're looking at it at. You would see the moonlight being reflected both here and here and smeared out over a whole surface. That is a perfect example of specular reflection. Same thing with viewing traffic lights that are smeared off over an asphalt surface, because asphalt is a little bit reflective at visual wavelengths, so on and so forth. When a surface is rough, it is still following the laws of reflection, but it is a rough surface, and so there's many different available options for reflection to occur. Moving right along. This is our first chapter on optics, and there's two basic types of ways to look at optics. First is called ray optics, where light is assumed to travel in a straight line. And the second is called physical optics, where light is assumed to travel more like waves, and that opens up the possibility of light interfering with other light and creating interesting effects that we're going to deal with in a couple of chapters. So, this is where we are right now. This entire chapter and the next chapter are very firmly bound into ray optics. Neither of these is a wrong way of looking at the situation, and indeed, there are wavefronts associated with ray optics. They would just look like this. Incidentally, probably unnecessary for me to say this, but I'm not leaving this material up on the board for particularly long because you have access to a pause button. And I'm hoping you'll use it if you're in a situation where you haven't gotten quite all the material off the board yet. So, ray travels in a straight line, does have wavefronts, that are perpendicular to the ray. If they were to encounter a surface like a mirror, by the way, that hatch pattern is the most common way for me to indicate a mirror. If there's ever any condition under which there's confusion, just let me know. Angle of incidence equals angle of reflection. And here's the wavefronts going away. You can even imagine each wavefront hitting and being forced back in a new direction. However, waves are not the main deal in these upcoming chapters. We are going to think of light as a ray for the moment, then we will come back to waves soon enough, and then hopefully unite the two of them so you have a seamless understanding of light. Doo-doo-doo-doo-doo. Hold on where I think where I am and where I want to be, and how I'm going to get there. All right. Before we move on to refraction, let's talk more about the implications of light traveling in a straight line and light traveling in a straight line after it reflects. The first idea I'd like to introduce to you is the idea of a pinhole camera. So, this is basically how it works. You have an aperture, you put a photographic plate back here, and then you hold the whole thing real still, and you wait for long enough for the photographic plate to be exposed to the point where it will develop when you immerse it in the appropriate chemicals. A question for you as a class, think about this before you move on. Would the image become sharper if the hole became smaller? So, think about it, pause the video, draw a picture of your own, and come to a conclusion that you are going to be able to defend at least to yourself, and then unpause. Pause here, unpause here. So, rays are coming from light bulbs and suns and light sources in the room. They're coming in all directions, but they have to follow the law of reflection when they bounce off your body. But because this hole is so large, there is a whole, no pun intended, there is a whole range of angles that could work. So this light ray is coming in from here, but I could also have a light ray coming in from here. And so the feet would get smeared out, the head would get smeared out, and it would all get smeared out. This is why to make an effective pinhole camera, you want to have the hole be as small as possible. The design difficulty that comes along with that is that the smaller the hole, the less light gets in, the longer you have to keep it holding still for exposure. This is how much early photography was done. Next example of an interesting reflective device. A plane mirror, which is what we call a mirror when it's flat. I'm going to put an object A, in front of the mirror, like a candle. Candles are great objects because they emit visible light. And then I'm going to have an observer here and an observer here. Does not really matter. They could have been anywhere. And they are going to look at the image of the candle reflected from the mirror. So they're not looking at the candle, they're looking at the reflection of the candle in the mirror. And then they're going to compare notes about where they think the candle is. And they're going to compare notes via a technique that's as easy as saying, I see the candle as being right there. And then the other person will say, I see the candle as being right there. And then the two of them will compare the way their fingers are pointing, stretch them forward until they cross, and that will be the location of the camera. This is basically how binocular vision works. So we know the laws. In order for light from the candle to get into the eye, it's got to follow this angle of incidence equals angle of reflection. So this person is going to point their finger this way. This is where the light is coming from their perspective. And this person is going to point their finger this way. This is where the light is coming from their perspective. And now we're going to extend the fingers out. And there is the image of A. No retakes in a recording. I didn't do this one great, but this should have been as far away from the mirror as the candle is, just on the other side. What did I do wrong? Well, maybe that's a more exact position of it. So there's the new image of A, but I still have it a bit off. This is that far away. This is that far away. I don't like it, but I'm going to roll with it because the tape is rolling. So this distance, A, is meant to be equal to this distance, B. When you are dealing with a flat mirror, flat mirrors create images that should be as far behind the flat mirror as the object creating the image is in front of the flat mirror. So that's a general rule that will hold. You can occasionally use to your advantage when you're working through either life problems or homework problems. I'm going to make much hay out of this later. Not so much right now, but this is a good time to note that this is your very first example of a virtual image. In a real image, the light that comprises the image actually goes through the location where the image is. In a virtual image, the light that comprises the image doesn't go through the location of the image. So the image is right there, but none of the light from this candle makes it past the mirror. Ergo, this is a virtual image because in the location of the image, none of the light that makes up the image actually gets there. I'm not saying you can't see the image of this candle. You absolutely can. I'm saying that the light from the actual physical candle never makes it to the spot where the image is and never gets resolved at that spot. We're going to deal with virtual images and real images with a lot more complexity going forward, but here's your very first one. It's a virtual image. Next example I do, next opportunity for you to pause in a bit, I'm going to set up just a regular plain mirror. And I'm going to put my generic stick figure admiring its reflection. And my question to you is, how much of a mirror is required to see the entirety of your body? If you have a plane mirror in your house, and almost all of you do in your bathroom if no place else, then this would be a good time to go and look at it and do a couple of observations. And then we're going to approach this from a more mathematical perspective, or a more geometric perspective at least. This person's height is L. And one of the key features on this person is that they have an eye. Now, the light that scatters off of the top of this person's head and the bottom of this person's feet is coming in from all angles. So you can have any ray coming off them that you wish, but only certain rays are going to be able to leave the top of the head and into the eye. And only certain rays are going to be able to bounce off the bottom of the feet and into the eye. I'd like you to pause this video and try to work out what distance of the mirror is required as a function of L given the rules that I just set out. And pause, and back. So, there's the feet. I need the ray to hit about halfway. And it comes back to the eye after following the appropriate law that the angle of incidence equals the angle of reflection as measured by the normal. And here is the top of the head. And I'm going to have a ray scattering off the top of the head and coming back in through the eye. So I put a normal here. Or I will in a second. And this is bisecting these angles into two right triangles. 4 right triangles, I guess. Do a tiny, tiny little bit of geometry. You should be able to convince yourself that the size of a mirror that's appropriate for seeing your entire body is just L over 2. So if you are 6 meters tall, you should be able to see yourself in a 3-meter tall mirror, provided it's perfectly flat relative to your body, which most mirrors are not. It also doesn't matter how close you are to the mirror. I'd like you to demonstrate this to yourself by repeating the exact same activity, but having the person be quite a bit further away and or quite a bit closer. If the mirror is mounted perfectly flat and the wall is perfectly flat, you should be able to see your entire reflection from all the way across the room to the very furthest reach at which you can see the mirror at all, to when you walk all the way right up to it, including when your nose is right on top of it. Well, maybe not quite that extreme. But this is the second, maybe third example of reflection we're going to go through. And I have one more for you. This type of mirror is called a cat's eye. It's 2 mirrors being held at right angles to each other, or maybe physically conjoined. It doesn't work anything like a cat's eye, but it's called a cat's eye because when light is shown into it, you can get a reflection coming back out of it. So I'd like you to see why. I'm going to give you a ray coming in towards this. And I'd like you to trace this ray all the way through the path it takes in this mirror system before it exits. So I'm going to go ahead and pause, unpause. Ray hits here, draw a normal, ray bounces back, draw a normal, ray comes out this way, and it is parallel to the direction of travel. So it is bouncing back in exactly the same direction that it bounced in, just being offset by a certain distance. A cat's eye. But of course, cat's eyes don't glow because the internal structure of a cat's eye is anything like this. Cat's eyes can glow because their irises can get very big and their retinas are maybe a little shinier than most creatures' retinas, maybe not. So normally I would hand you these mirrors. That's obviously not happening during COVID. So let's explore a little bit. Here is a regular mirror. I'm going to move it. This worked much better when I demoed it. I'll just move my finger closer. Like so. Now I'm going to take a cat's eye mirror. Repeat the same procedure. Notice any difference? Even though you could just rewind, let's do this one more time. What, if anything, do you think is going on? I will ask you about it in class. And then here is a somewhat more complicated structure. I'd like to invite you to think about what's going on inside of this thing. And anybody who can tell me what the internal structure of this is will impress me greatly. They will not get extra credit, but I will think that it is very impressive that you thought so deeply about it, and I will give you accolades for it. We are now done with all the examples of reflection that I'm going to do in this class. And also, I forgot to set a timer, so my apologies if I go long or go short or anything like that. Refraction, you need to remember that this one doesn't work. Refraction is what occurs when light travels from one media to another. Provided that they have different indices of refraction. For example, if I take a glass rod and I stick it into a container of glycerin, I don't see anything. Literally, I don't see the glass. I don't see the rod. I don't see the glycerin. Because the index of refraction, whatever that is, of the glass pretty much perfectly matches the index of refraction of the glycerin. No change of index of refraction means that light doesn't do anything interesting at the medium in between the two. Now, having said that, I now have to define what index of refraction is. So, the index of refraction is a qualitative measurement of how much the apparent speed of light changes when it goes through a medium. It is always 1 if you're in a perfect vacuum. It's pretty much 1 in air because air is not all that dense. If you're ever doing a problem involving air, feel free to just set the index of refraction to 1. It's about 1.33 in water. It's about 1.5 in certain forms of glass, so on and so forth. The mathematical formulation of what the index of refraction is would go something like this. So where c is the velocity of light in a total vacuum, and n is the index of refraction. N is 1 for a total vacuum. N is approximately basically 1 for air. N is about 1.3-ish for water, so on and so forth. N is, I believe, ridiculously high for diamond. Which, as you'll see, once we're